Hello everyone and welcome back. In this video, we are gonna learn together how to simulate a bolted assembly in ANSYS Workbench, and we will learn it together step by step. As you can see on the screen, we have two beams, which is the vertical one and the horizontal one. At the end of the horizontal beam, we have a downward force, which we will see it in a moment, which is in the positive x direction, downward force acting, and we will see if the bolts are okay or not under the investigated load there. So let's get started. So for this model, first of all, I'm gonna put you on the description the link to the geometry so you can practice it with me together, or you can investigate this performance of this beam under different loads by yourself. But for now and for learning purposes, let's see the geometry together. So this is our geometry. As you can see, I'm planning actually to put a fixed support on this bottom face and a downward force on this end face of this profile. So in this analysis, what we have actually to prepare first of all, you have only the parts, the steel parts, which is the profile. So what you have to do or prepare in the geometry phase is to model the beams, which is represent actually the bolts. Because we have multiple bolts at these locations and it seems to be stiff enough for us, so modeling the bolt as a beam will be enough for us to represent actually the load acting on that bolt and see if the bolts are okay or not. So in order to model the bolt as a beam, all what you have to do actually is to first of all to describe the under or the contact between the under bolt head and this plate through modeling this split faces. As you can see, the small rings. You can do it just by clicking on the surface, design and sketch mode, and from there actually you can just go to circle and draw a circle, and it's actually for our now bolts. They are M6 bolt, so they have underhead bolt area of a diameter of 8.9 millimeter, and you can do it for every bolt until you finish it. I already prepared that for you, so you can find this file in the description as I told you before. But after that, after you prepare this surfaces, you have to model the beams, which you have to draw points on the center of each hole that we have here, and extrude it actually enter the end of our thread, which is in my situation here is until this location. So we have at the end this beam. After modeling these edges, you have to give them a cross-sectional area, and that you can do it by going to prepare, and from the profile feature there, you have to create, first of all, it will be empty, so you have to create a profile, and after you create a profile, you have to go to beam profile and right-click on it and edit beam profile. And from there, you give actually the cross-sectional area of your beams. In my case, it's M6 bolt. It has around a radius of 2.53 millimeter. After you finished, you just exit, and you will have then this M6 cross-sectional area. So you choose all the edges you already drawed and go to actually you go to prepare profile and you choose your cross-sectional area. After doing this, so you did actually prepare the model. You did prepare the regions where we have to connect our beams to these surfaces, and the beam themselves to represent the bolts. After finishing these stages, we are finished with the space claim, so we can go directly to the workbench and prepare the setup of our analysis. So for the setup, actually we are using first as a material for everything, for bolts and profile, steel structural. I already changed the air modulus from 200 gigapascal to 210 gigapascal. To do this, all what you have to do to go back to the schematic, you go to the engineering data. And by going to the engineering data, if you have like only the structural steel in your case, so I did like change the Young's modulus there from 210,000 megapascal to 1000 megapascal to 210, which is by default in ANSYS is 200,000 megapascal. In my case, I like add 10,000 on it. So after changing this, it's not like a must, it's like depending on the material that you used in your simulation at the end. So after we have the geometry, we have the right material already like specified for every part that we have here. What you have to do actually is to create contacts and joint for the bolted connection that we have. In this simulation, I already have two groups. Actually, I have just this profile and this group. I already prepared this in a space claim, so this group will be like every part of it like welded or glued together through something called like share topology. By putting all these parts in one group and enable the share topology features, I can show you this in a moment. As you can see now, this group actually is all of these parts are under this group, and this group is the share topology already enabled. So if you go to Workbench and click on the share topology or show connected bodies, you can see clearly that these profiles plus these diagonals are like welded together with the plate. The other profile is outside, so it's not relevant, so they can actually like move move from each other. So we have to define like a contacts and joints so they are not like falling without any load. So let's go back to the simulation model, and in order to check this, actually you can see like an important feature inside ANSYS. If you click on the geometry and go to display, there is something called like explode view, and when you like move this cursor, you can like explode your model. What we benefit actually from this, not just showing that our model is exploding, we can show also all the group if we have like any part which is not inside the share topology. So we will see it like he will like explode like alone and go in space alone. What we are seeing right now, we can see like the overall this like group, it's like explode together, which is mean like they are glued together, just like as a check for now. We have the beams, also they are like separate, and this profile. So this is like just like a small check to see if our share topology is right defined. After like doing this check, first of all, you can like generate or create a contact, which is in this like situation a frictional contact. It's like just by clicking on connection, insert, and from manual contact region. After you click that, you get a contact. You change it from bonded, because an ANSYS bonded is the default one. You change it from bonded to frictional, for example. And I did give it like a frictional coefficient of 0.12, and I did like change the interface treatment to adjust to touch. So let's like move a little bit the explode variation. So as you can see, I did like choose this face as my contact and this face as a target face. So after you define the contacts, so all what you have to do actually, or remains to do, is to create that joint, which is like connected the beam to our structure. And because we have like many bolts and not just one bolt, so it's not like efficient to do this like manually, like step by step. So in this case, or in other cases where you have like 100 of bolts or 1,000 of bolts, there's like a strategy that you can use in order to do it like an efficient way, faster and practical actually. So I will show you like now like how to do this. In order to create these joints like so fast and in an efficient way, what you have to prepare first actually is to prepare a name selection, the beams that you have, this will be like effective if you have like many bolt size in your model. We have to define the vertices, like the end point of each beam in name selection, and we have to define these faces, which is which I want to bond the vertices here to this faces to connect my beam to this face, and the other on the other like side to connect these vertices to my thread actually, which is this face. So in order to do this, you go to model, and from model you click on right click, insert and name selection. After you click on name selection, you will have like in the tree a name selection, and from there actually, as you can see, I already like prepared like many name selection, which is like M6 edges, which is represent here, as you can see, all the M6 edges. I have the vertices, which is represent only the endpoints of these beams, and M6A, which is represent actually these faces, the head faces, and the other name selection, the final one, which is represent actually the thread faces. So do I have to choose these faces like manually? Actually not. And that's why we are using name selection. So in order to do this, I'm gonna to redo these like together, so you can see it how to prepare this and do it do the same in your model. So first of all, to do a name selection of our all edges, or what you have to do from name selection, insert name selection. After you click on it, we click on it and we change. Actually, I will like do it again. So name selection, because I don't have to select anything before I click name selection. Now I click name selection. I changed the scoping method from geometry selection to worksheet. Let's make it bigger. And after that, you have to add on the action there. Add. I'm going to choose body. From criterion, I gonna choose a cross section, so I can choose which cross section for this body I want. I will click on it and equal, and from there I have M6. This is actually what I did prepare like before in space claim. From the profile I named there like M6 in case you didn't name it, so it will be like the name of your faces there in space claim. So when you click on this cross section, or if you have many cross sectional areas, so you can choose everyone from this like list. In my case I have only one, so M6. And from now, if I click actually on generate, you can see that he generate or selected 14 bodies, which they are like the 14 bolt, but they are as a bodies. And I want these like edges, bolt or bodies to be as edges. So to do this, I click another one more time on the second row, change the add to convert to, and actually what I'm doing now is I'm telling him that I want all these bodies that have cross section area of the M6 bolts and convert them to edges. I click again on generate, and as you can see now I have the 14 edges already selected. So in case you have like hundreds or thousands of bolts, this will be like so efficient to do like this. So like this, we have now name selection. You can like rename it to M6 edges. If you wanna like now to do like or to choose the vertices of these edges, all what you have to do is to duplicate what we did here and only change the edges to vertices or vertex and generate. So you can see now you have the vertices. So in the next step, in order to name all these faces, what you have to do, we go actually to name selection, insert again, and we change the geometry selection to worksheet. From there I add, I tell him that I want faces, criterion size, and equal to. So I go now to my faces, I just click on this face, So I can see down actually how big this face is. Now my unit is in meters square, so let's change it to millimeter. To do this, I go back to home, unit, and I'm gonna change the unit so you can see now it's my area in millimeters square. So I have to put this value actually in this cell. So let's write there 33877 and generate. You can check on the screen right now. You can see like all what they are in red. They are the selecting one, which is correct, or what I want actually. And I have now 14 faces. So now you can rename it as like M6 like faces. To do or to choose the thread faces, you do the same, but instead giving the size of this face, you give the size of the thread, which is like 94128. So what you have to do, duplicate this, and actually we change this value to, I click there and I change it to 94.128 and generate. So now you get, as you can see, all the thread faces are already like chosen on this name selection. So perfect. After you finishing all these steps, you are now ready to generate these joints. It seems like it took like some times, but if you are like, now we are like for learning purposes, I'm trying to teaching you like this like step by steps with all details. With practicing, you will do this actually in less than 1 minute, the whole thing, and that will be actually like so efficient and practical. So we need all these like what we have. I will delete this what I did now because I already have them like on the first 4 name selection, as you can see. In order to generate that joint that we have, so as you can see, we have to create a joint which is like connect this vertex to this face and the thread. In my case, I have 14 bolt, so I have to create actually 28 joint. If you wanted to do this manually, this will take time for sure, and you could like make some mistakes like in between. So how to do it efficiently? So we prepared the name selection. Now I'm gonna like try to create a joint with you together so you can see it, how to do this. Let's like hide the ruler. And for now you go to connection actually and insert and joint. All what we have to do actually, I go up and choose like vertex, and I have to give him just one example like this. I choose vertex, I choose for example this vertex and choose it as a reference, so I click on reference. After that, this vertex should be bonded or connected to this face, so I have to go back to face and choose this face and choose it as a mobile face. I let everything like as by default, it's like okay. So as you can see, we have this joint now. I can do the rest like the same in the same way also for the thread ones, but they are like 28 one. And in other cases where you have 100 of bolts, this will take like too much time. So how to make this like faster and do all the rest of this bolt the same but automatically? Actually in ANSYS we have a feature called like automation, which we can use it, and it's like so important. All what you have to do is the following: is I click on my joint that I want to automate, which I did before, and as I told you, this is my example, and I go back to the top there and choose automation and object generator, and from there you can see that we have to choose a reference. From reference, if I click on this list, you can see all the name selection that we did prepared before. So the reference for me is actually the vertex for this edge, which is M6 vertices, which I named before. So I choose it. From the mobile, I want these vertices to be connected to these faces, which is in my case the M6A already named. Now, before you click on generate, you have to define a minimum or maximum value. In my case, this like distance is actually the distance from the vertices to the plane of this face, which if we look from the Z direction, it's actually on the same like plane, which is 0. But to make sure that all like joint will be like generated correctly, I'm recommend you to click or put 1 on the maximum cell there. So we click 1 there. Every time like you do it, you can like take it, it will be like enough actually to find all the joints. We click on 1 and just I click on generate. As you can see now, in 1 click and so fast, I have now on the tree all these 14 joint like created in 1 click actually. Now what I have to do also actually is to generate that joint from the other vertices sides and the thread. I do the same strategy, so I go back, click on join there, I right click, insert and joint, and from there I choose vertices. So vertices, in my case here I make zoom in, so this is my vertices as a reference. So I have always to teach ANSYS, like I have to give him just one example. So I create this vertices and choose this thread and as a face. And now actually, as you can see, this is a bottom. So you go back to automation, object generator, and now I still have the same reference, the vertices, but instead of this faces, I have to choose the name selection, which is like took the thread into consideration, and in my case I will have to change the M6A there to M6G, which I name it. Now for the distance, actually the distance should be minimum, actually the distance from your vertices to the middle of your like actually your face, which is in my case actually 4 or 5 millimeter will be enough. Don't worry, in case you click on generate and nothing comes out, that means like your maximum was not enough, so you have to make it like to increase the value so you can like try it again. So in my case, let's like click 4 millimeter and hit generate. And now if I choose all of them, you can see like we did like all these connections like automatically in 1 click. So now if I click all these joints, you can see clearly that we have 28 joints already defined so quickly, so fast, practical, and efficient, in an efficient way. Like this, actually, you have to model the beam bolts in ANSYS, especially in cases where you have like a lot of bolts. Now, actually, after defining or preparing the model, defining the contact, the joints, the next step is actually to generate a mesh for our structure. So for my case, actually, I already prepared the mesh. What you can do it actually the following. So in my cases, what's important actually for you to know is the following. Like I change the element order from linear to quadratic. This is first things. I recommend every time like to use quadratic. I did give him an element size of 7 millimeter. And I choose actually the mesh sizing as adaptive and choose like span angle center to medium just to capture when we have like some radius automatically. But actually I already like defined or choose all these faces. So if I click on this face sizing, I choose all these faces that you can see in blue and give them like a element size of 2 millimeter. Actually, these regions are important for me because there were where I have like these bolts where I have to capture later on the axial force and shear force acting on these bolts. So they have to be like a little bit fine as a mesh in comparison to the structure itself. You can do it like so fast. You can just click on this plate and hide all others. Just give you an example, and you can change the mode from single select to box, and you can just like choose this box. And as you can see now, you are selecting all these faces. You take these like out, these faces, and you have the 56 faces, so you don't have to click on it like face by face, of course. Like this, you can like select them like all faster. After you select these faces and choose like a suitable element size, in my case I did take like 2 millimeter, you can also, or you have also like to give like edge sizing for your like bolts or beams, because by default they will be not enough actually in most cases. So in my cases, what I have to do actually, I have like in my model solids and beams. So on the screen, you can right click on it, hide and hide solid, and you will still have just the beams. You go to edges, mode, box select, you select all the beams, and you can enter their sizing, and you will get edge sizing. After you get this edge sizing, you change that type actually from element size to number of division, and depending or looking onto the length of your bolt, you can choose like something like enough for your bolt size. So at the end, it's depend actually. It's not like a fixed or recommended value. It depends if your bolt like is smaller or bigger. So you have to make the number division like lower or higher. In my cases, like I choose like 15 number division. That's mean like he divide the beams into like 15 section, which is like 15 element in my cases, and this is like will be like, I believe that will be enough in my case. So after you prepare all these settings, or what you have to do, right click on the mesh and generate mesh, and you will get something like look like this. As you can see now, we have like a group like or coarse mesh like overall. In the region of the bolt, it's like a little bit like finer, as you can see, and the beam itself, they are like fine enough. Now, after finishing the mesh phase, what we have also to do actually to define the boundary conditions. So, for the boundary conditions, if I go to display the boundary condition and go there, the boundary condition, as I told you on the beginning of this video, I did plan like to put a fixed support on this face. So I click on the fixed support. I did choose this face to be as a fixed support, and I did put a force, a downward force actually acting on this end face of this profile with like around 10,000 Newton, which is like around 1 ton of load actually acting downward there. And the goal of this simulation is to check the bolts if they are like from size and strength class are enough or not. We are gonna like to evaluate the bolt according to VDE. Not in details, as I'm gonna to show you like the results at the end, the safety factors like against yielding, like shearing and sliding. In case you wanna like to learn like in details how to get like these safety factors, I will put you also on the descriptions a link to every one of these videos, so you can learn how to get these like safety factors according to VDE 2230, which is like a standard or norm mostly used or famous used in Europe actually to check bolts to see if they are like okay or not. So in my case, after defining the fixed support and the force that I have, I still have to define a bolt pretension for every edge. Also from here, like I can also benefit from this automation because I have like 14 bolt. So what you have to do actually from the static structural, you insert actually a bolt. So you bolt pretension, and when you take the bolt pretension into consideration, so you have to like to calculate at least like 2 steps then in your simulation. We will go like in a moment about it. Just to create in step one the bolt pretension. After that, in step 2, should the load comes in the simulation, it's not recommended to do both of them in the same step. So at step 1, you define the bolt pretension and load at the same time. This is not recommended. So please like separate this in 2 steps at least. So in this like to define the bolt pretensions, all what you have to do, insert bolt pretensions. You give the bolt pretension for your bolt. In my case, it's like M6 bolt. According to VDE, it should have, and for 90% like of the yielding strength of this bolt, if it's like 8.8 strength class, it's like around 10,200 Newton. So you give on the first cell 10,200 Newton, and in the step 2 you change the load to lock. So in step 1 he like reach this like value, and he will remain on the other steps like the same when you are clicking lock. In case you have like more than 2 steps, so you have to change all the steps down from load to lock. So after defining the value and set up the bolt pretensions, you have to choose the bolt pretension on which edge actually. So I go to edge and choose this edge, for example, and choose it. So you can see now on this edge, now I have a bolt pretension. So of course you can do it manually for the other 14 bolts, but we will not do it like this. It's not efficient. So you click on your bolt pretension, go to automation, object generator, and from there, from the graphical selection, you choose your M6 edges, which is all the edges that you have on this model. After clicking on it, I click generate, and you will see on the tree to the left side that I have bolt pretension for all other bolts, as you can see, done like in one click. So this is like impressing. As you can see, it's like practical, and now we are ready actually to simulate our model or to solve the model. So all what you have to do actually, before we solving the model, before I forget, actually you go to analysis settings. As I told you, we have at least to define 2 steps, so number of steps 2. I did like actually enable the large deflection to get like most realistic like results as much as possible without any like assumption like or like for more accuracy of the results. So in this calculation we have bolt pretension, we have everything defined, we are ready actually to hit solution and solve. I already like did this for you guys, so the results will be as you can see now. This is the same model, same load, and as you can see now we are seeing actually the total deformation. It's like a bit exaggerated here, it's like 50 times exaggerated. Downward force, this is like the equivalent stress in our model actually. And what's important for us now actually, other than the stresses on our profiles actually, is the axial and shear force acting on our bolts. And because we did like models the bolt as a beams, so we can benefit actually from that, and from the solution we can insert the axial and shear force directly. So if I click on axial force, you can see directly on the screen the axial force on each beam actually, on each one of them. But you have to know that the forces that we are like seeing right now on the model, they are like including the bolt pretension. And if you click on the total shear force, you can see the shear force on each bolt of them also. Like we see like the down bolt, they like experience like higher like shear forces and so on. Now like this actually we did simulate this bolted connection as using Workbench, and we did like step by step. Now, in case like you are interested to see like how if the bolts are okay or not, so what we have still to do actually to duplicate this analysis. So you have to go back to ANSYS schematic, as you can see, and this is my first actually analysis. I did duplicate it. So how to duplicate this? You just click on this arrow and duplicate. You get a new analysis, and in the new analysis actually you will you don't touch anything. All what you have to do is to suppress the bolt pretension that you have did before. So we don't need the bolt pretension, and because we took them out, so we need just one step then to calculate this model. So I go to analysis settings and change it from 2 to 1 step. And the force, actually I don't have to forget this. the force, you have like to put the force on the first step, because we are like loading our model from the first step, because we don't have like a bolt pretensions. Why we do this? We do this actually just to see the external force acting on the bolt, and this is the way how to do it. So you have to do it without taking the bolt pretension into considerations. In the first analysis, we took the bolt pretension into considerations to know the shear forces, and to know the external force acting, you have to suppress it. So of course, from this analysis, I can also see the shear forces, but these values actually are not correct. So the correct values for the shear force are with the simulation with bolt pretension. From this analysis, all what I get actually is the axial force, or all what I have to know, the axial force. As you can see from this analysis, these forces actually are the external forces acting on each one of these bolts. So I took the highest value from there. I took the relevant shear force for this bolt from the other analysis, and I did actually like took them and like see like according to VDE how these bolts actually or how much safety factors have these bolts. So as I told you before, I use like M6 bolts here with a strength class of 8.8. According to VDE, I have a safety factor of 1.129 against yielding. For this, like the maximum like loaded bolts in my model, of course we have bolted that they have like larger safety factors, but in our design or like if every time we took the most like loaded bolt, and according to it, like actually we design our model. So we have 1.129 against yielding. We have safety factor of like a high safety factor against like shearing of 72.6, and against sliding we have like 8 against sliding. And yes, actually these values are like enough. Actually they are okay. We are not like critical, and somehow they are okay. We have like a high like safety factor against shearing and sliding, because actually these two bolts, if I go to the first model, okay, we see that we have 700, but our axial force, they were like these bolts, and this bolt they had like actually around 100 like 20 Newton as a shear force, and that was not like too much. Yes, in case you wanna like to learn how we got these safety factors like exactly in details, as I told you before, I will put you on the description the links to these videos, so you can like learn them like in case you are interested on them. So as you can see on these videos, we learned how to simulate a bolted connection like using ANSYS Workbench in detail, using the beam approach of modeling of the bolts actually, and we evaluate the bolts, and under like 10,000 newtons our structural like actually it seems like okay. It seems there is no need to optimization actually, and we can like investigate further like other things. So if you found this video interesting, like I hope like you learn them. In case like you found something like so fast in this video, you can like pause it of course, and like practice it like again and again. If you have like any questions, we can put them of course on the comment sections. If you found this video helpful, subscribe to that channel and like the video, so we can continue like posting like more interesting videos, and I will see you in the next video.